Okay, so what are we going to talk about? I mean, I guess there is a time itself in all these networking workloads and on devices has become quite an important aspect, and being able to achieve precise timing or time synchronization as well as workloads such as high frequency trading, which depend on um, exact time scheduling and low latency kind of through the pipeline, low latency guarantee through the pipeline. Is some of the interesting workloads and devices are getting changed to support these requirements. So I will be talking a few of these um, you know, workloads that we have seen. A couple of them are related to high frequency trading. One of them is just basically once you have those kind of features, it enables some other um, fairness and avoiding burstiness in it, which results in avoiding congestion ultimately, and packet drops, congestion due to packet drops is some of the things that we're going to talk about. And with me is Priyali from Intel as well, who's going to cover portion of the talk. So, what do we have? We have what is the requirement on a device for high frequency trading and the use cases, as I mentioned. So we'll go one at a time on those. So here is what we understand are requirements from the NICs when it comes to high frequency trading, being able to achieve very low latency for the HFT flows, and not just that, very tight tail latency, very low jitter, so that there is predictability and um, timing requirements that get met for the trading transactions. Um, Being able to isolate these low latency flows and prioritize them through the device from the rest of the general flows. Of course, in order to, you know, be able to monitor and log that the packets were actually um, you know took the amount of time they took on the device, you do need PTP, PTM, time synchronization kind of features on the device, and in general flow identification. The other requirements for high frequency trading is being able to support inline crypto of these packets as they need to be um, encrypted as they leave the client machine and decrypted when they reach the client machine. Some side requirements like multicast application for um, being able to send uh, market data updates to a large set of clients. Um, that's the high frequency trading requirements. So I'm going to take a particular uh, setup that we had to do for this workload. In this case, what we're showing is um, there is two kinds of flows that the device has to deal with. A flow that starts from the client, which is doing the trades, and the server, which is either sending responses or market data or another or other general traffic coming onto this box. So there are a few things that are needed for the device to be able to achieve. Again, in this scenario, Linux is in picture only when it comes to being able to set up, um, the DMA queues, for um, the data plane versus actually most of the data plane is being dealt with in the device itself. And Linux is also helping with configuration of the device and control plane setup for identified flows and things like that. But and monitoring. But in this particular use case, there's not much of actually no data flow going through the Linux machine or through the CPU. It's all dealt with in the device. So let's look at the bottom flow. The bottom flow is a client originating a trade, which needs to go through precisely a low latency path and be able to encrypt the traffic as it goes through the smart NIC or the IPU. And the other flow on top, the green one coming from the server, it doesn't have any strict latency requirements, and it just needs to be separated out from the other flow on the device, so it does not cause head of line blocking for the low latency flow, as well as um, um, it needs to be decrypted as it comes to the client side. So those are the few things that need to be done. So so how do we achieve this? Both these flows, as I mentioned here, are port-to-port flows within the device. So the Linux drivers set up queues with memory buffers to be able to do this hairpinning of the flows within the device itself, and that's what is going on. In order to have fixed latency for the HFT low latency flow, instead of using the memory from the host memory for these queues, we end up using the on-chip memory, the OCM memory, which is on the device. And so it does not really cross the PCI boundary, which is where the PCI latency jitter happens, where it's going to the host memory. The PCI latency observed can be varied from one transaction to another. So so the port-to-port queue, DMA buffers, and the ring itself, they are separated out into two different kinds of memory. And then the device has to be able to classify the packets for these two flows separately, so that it directs it to the right queues and the implemented on different memory systems. So that's so being able to classify, and then also that classification helps in separating ordering domains within the device, which is more like saying parallelizing the processing of these flows, where one is not blocked by the other, more so the one that is the HFT flow, so that it does not absorb any delay because of the other flow. The last, so inline encryption and decryption here, I'm showing an example with PSP, which is supported on the device. And then, monitoring is the last piece that is important here, that for the customer records, that it was actually, fixed latency absorbed for these flows through the device. Um, that's one of the aspects of the few things that we talked about earlier. So being able to do low latency and uh, low jitter, plus being able to um, identify the flows and timestamp for records and things like that. Um, um, okay, and um, yeah, this is just kind of write up just to help me not forget things at this hour. Uh, okay, so there is the second uh, workload that we had to implement on our devices, and this is um, can be used for HFT as well as for other use cases. So let's understand what was the requirement and then how do we achieve this. So this was where a large number of flows had to be delayed by varied amounts through the device. Now, the exact challenge that you know the customer was running into and why they needed an offload was they were not able to achieve the scale they needed for the flows without the offload, and the CPU cycles were busy waiting to send the packet at a precise time. So with the hardware being able to do a flow identification, being able to um, you know uh, park the packets when the precise time comes to send the packet out, and then it just um, you know, the delays for the packet by ALU operation. Those were the few things that we did for achieving this requirement on the device. So, uh, so there is, before we understand the complete flow requirements, a flow through the device, I want to talk about certain hardware blocks that are essential to be able to achieve this in the device, the per flow fixed delay for the packets. So there is, and this was something long back proposed by Van Jacobson in one of the keynotes in Netdev, and this is built into our IPU, um, uh, um, uh, hardware IP called the timing wheel, which basically, after a packet is classified and you've determined the time to launch a packet based on either a flow rate or something that got calculated, like a delay addition, like as I mentioned, a fixed delay addition, which determines when the packet, after it has reached the device, after how much time it needs to be sent out or scheduled. Um, this is this particular hardware block helps in um, storing, the packet context in different um, uh, time slots, which are then, when the current time is the same as the time slot, the packet can be scheduled. So it requires, um, this um, this kind of a design in hardware where you could park packet context after you have classified them and done the packet processing for determining when they need to be launched. You could park these packet context waiting for the time to be sent out on the wire. Um, of course, there are cases where you don't want flows to be um, um, paced or scheduled at a later time, and you just want to bypass That's also something that um, this design allows for. Um, I mean, yes, that requires being able to credit count all um, um, the phi um, um, credits that are available for on the wire. So this particular flow, the way we implemented it, I mean, there were some more requirements from the customer to kind of be able to make it transparent for the application. And so what we ended up doing is uh, implementing this on the embedded course. I mean, ignore on the picture it says host. That was basically just for POC, but ultimately this gets deployed on the embedded core um, Linux OS, where uh, packets sent from the host are um, 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 sent through to the embedded core for um, the XTP, AF XTP queues to be able to um, inject the actual delay requirements for each flows without the application being aware of it. Um, so yeah, so this is the picture. There were uh, again being able to um, use like the busy pole with XTP and zero copy allowed for um, um, uh, you know using the complete CPU cycles for dealing with large amount of packets to be to be um, um, uh, marked with the right delay to be dealt with in hardware. So uh, and yeah, so we did instrument make some changes in AFXDP, which is something that um, would be very helpful as we see with EDT and other things as well. That we ended up implementing out of order processing for AFXTP because multiple flows going onto the queue, they are delayed by different amount of time and they can um, uh, they will end up completing at different times. So they need to be focused differently instead of being in schedule in inline in order completion, and that is so that we do not have to have very large uh, transmit queues and reuse the same queue multiple times to schedule the packets to the device. So yeah, so um, this picture is basically just showing that the work is submitted using XDP, Visipol, zero copy sockets on the embedded cores, and then the packet processor calculates first classifies the flows and then does the uh, calculation for time to launch by adding delays for each of the flows, anywhere between 2 microsecond to 200 microsecond, and then giving it out to the timing wheel so that it can then, um, keep the packet context while um, uh, the time to launch that packet arrives. So there were some interesting changes that are required in the queuing model to achieve this out of order completions, as well as being able, these are the same things that we propose for AFXTP queues to be able to handle out of order completions. So what this picture is showing is you have the time instances of a transmit queue on top, um, where you go through multiple rounds in the same transmit queue, sending packet 0 to n times 2, um, uh, shown in different colors, and they are getting completed in a in, since they could be delayed for different amounts depending on which flow it is, that they are completing out of order, and the completions come in a completion queue, which is separated from the transmit queue. And the completion queue gets two kinds of completion. One is the descriptor completion, the other is the packet buffer completion. So descriptor completion helps you in wrapping through the transmit queue multiple times to continue posting packets to the device, while there are packets waiting and filling up the timing wheel and not yet scheduled. Whereas the buffer completions, which are individual, packet completions, would then uh, be, uh, you know, will separately deal with the freeing of the descriptor, the packet buffers, um, you know, um, uh, decoupled from your descriptor, um, um, you completions. So that's the whole idea here, that AFXDP queues can be extended to support a different queuing model, which supports out of order completion. Um, and we introduced a new API. Of course, none of this work is upstream, but this talk is basically to say we would like to send these patches out if this would benefit um, um, other use cases for timing wheel. And yeah, so right now, the AFXDP TX completions, they are batched, and they're not individual buffer completions, and that's to achieve very high throughput. And this one's because the buffer completions are separated from descriptor completions based on when a packet is scheduled. This new API introduces the out of order um, completion per um, uh, XSK frame. Um, and then there is a helper function as well, which helps in peeking through the completion queue to figure out if there are descriptor completions posted, so that you know continuous posting of more packets can continue and wrapping around the transmit queue while the previous packet are not completed or not scheduled. Um, so these are some of the extensions in AFXDP that we have to do to be able to achieve this precise flow, fixed delay of the packets, a different one per flow. Um, and I think Magnus, who's not here, he would be sending out a patch to or two to support this in AFXDP um, um, code base. So yeah, so that's pretty much the second use case which needed for flow fixed delays. Again, what is important is features like being able to synchronize the device and the system time, like PTM, like that was discussed in the previous talk, so that you know, um, um, uh, time stamping that happens in the device and the delays that get added are accurate. I will hand this over to the last flow that Priyali will talk about, and that's more about earliest departure time and enhancements in Linux. to support it. Sorry.
Okay. Yeah. Thanks, Anjali. So yeah, third use case is having EDT earliest departure time. So application may need to schedule the packet at a certain time. For that, to leverage the timing wheel offload, where queue scheduler is modified along with our IDPF driver for the IPU. There are multiple ways in which timestamp in the SKB can be inserted. Like there are options like SOTX time, TCP, TX delay. These are socket option, and there are pacing rate which you can set on the flow. So SOTX time is a way where you can exactly tell at which time packet should be transmitted. TCP TX delay is if you want to add a certain delay for each packet. And pacing rate can dictate that how much delay should be between the packets, maximum delay between the packets. So uh, apart from this, congestion control algorithm or any other algorithm running can modify the SKB timestamp depending on the congestion window or round trip time. Um, so yeah, once like as a timestamp is inserted by the application from the upper stack, it comes to the scheduler. So fair queue scheduler is right now getting modified to support the timing wheel hardware offload for EDT. So timing wheel has a parameter called horizon. So horizon is the time length for which uh, timing wheel can hold the packet. So this hardware horizon is advertised through the IDPF driver to the scheduler. So a new parameter in the FQ scheduler has been added called upload horizon, which is uh, basically which must be less than whatever um, hardware horizon value is. So right now, like we have 128, 256, and 512 millisecond horizon. And FairQ scheduler can choose any value less than that. And FQQ disk also supports this max rate, which dictates the pacing. So result of upper stack and the pacing rate timestamp is inserted inside the SKB. So once SKB reaches the schedule FQ layer, FQ enqueues the packet inside its tree based on the SKB timestamp. Once packet is scheduler is scheduled for the DQ, it DQs all the SKB which are within the offload horizon. So basically, if packet has the timestamp which is lower than current time plus the offload horizon value, those packets gets scheduled for the next phase, and rest of the packets are flow get throttled to be scheduled later. So after dequeuing from fair queue disk, once packet reaches to the IDPF driver, which is our NIC driver, it uh, it converts the timestamp to the device time format. So upper stack uh, right now TCP and other entity are using monotonic timer, not real time. So a conversion is needed from monotonic time to the device time. Once this conversion is done, the timestamp in format of device time is put in the descriptor, which is forwarded to the timing wheel. hardware block, and depending on the escape time, uh, it gets inserted in the time slots. So timing wheel, as Anjali mentioned, timing wheel maintains the various time slot and for various granularity. Um, so yeah, and then timing wheel transmits those packets when that timestamp has is matched. So if a packet has a timestamp before horizon, then it gets scheduled. Otherwise, for beyond horizon, packet gets dropped. But beyond horizon is usually not possible because that is taken care by throttling in the FQQ disk layer itself. Right now there is a gap, like converting monotonic time to device time is a challenge. Usually PTP stack means any means PTP tools you run to sync this real time to device time. So I think in the future we will be adding support in the IDPF driver to convert this monotonic time to the real time, assuming that PTP application running in the background will do the device time sync to the real time. So because reading device time for each packet is not efficient, so with the assumption that PTP stack will be running syncing the device time in real time, then we will just read the real time, convert the real time to the monotonic time. So that will be done in the future. Yeah, Anjali, please can you go to the next slide?
Really?
Yes.
So beyond PTP, you also need PTM, right? Because
Yeah, I'm going there. Thank you. So yeah, so for synchronization device or synchronization of device to device clock and real clock, there are ways, it's PTP software ways, but we recommend the PTM PCI capability, which has better accuracy and low latency for synchronization. I will explain how it is done in the IPU in the later slide. Uh, yeah, Anjali, please go. Next one, please. So, uh, EDT can be done in the software, purely in the software also, but yes, it has holding the packet and consuming the CPU cycle is expensive. So with the hardware offload, we free the host CPU and CPU utilization goes. We see the CPU utilization is better and throughput is also better because of the overhead of schedulers switching back and forth. So these are the few benefit of the hardware offload in these use cases. Yeah. So as previously mentioned, we recommend using PTP for the accuracy, PTM, precision time measurement protocol, which is a PCIe capability. So in the uh, earlier it was talked that how PTM work. So PTM messages are sent over PCIe periodically by hardware without any software overhead. So our CPU running its own TSC clock, and TSC clock copy is so ART is always running timer. So a copy of always running timer is sent over PCIe to the device, and when software or means PTP software which implements this PTM capability wants to read the do the cross timestamping to read the device and art at the in an atomic way. A PCI strobe is generated, and on the PCI strobe, the art copy and device time was captured in an atomic way. So that results in a great accuracy to get the snapshot of them together, both timer together. Earlier, like software method was used where it was not possible to get both device and CPU clock at the same time in an atomic way. So PTM provides that capability, and to implement this PTM capability in IDPF driver, yes, cross timestamp framework is used. So it driver has implemented NDO ops for this. So in the worst case scenario, we have means our hardware folks have managed to measure the PTM accuracy versus PTM accuracy. So in worst case, if we use the software mechanism to get the timestamp of both CPU time and the device time, we have seen that inaccuracy of around 1 microsecond. With PTM, the accuracy was around 400 nanosecond. So we recommend if we are using the high frequency trading use cases, PTM should be a must. Anjali, next one, please.
Okay, if we can wrap it up sooner than later.
This is the last slide. This was just for completeness. Maybe I'll just go over it very quickly. So as I mentioned, some other high frequency trading requirement was multicast replication, which is something supported. It can be exercised through TC filter mechanisms to match on multicast address and to mirror to a particular or interface. This is standard there in the kernel and can be offloaded onto the device. That's pretty much it. And that's it. So.
Again, thanks for showing up at this time. Questions?
Thank you. In your presentation, it was mentioned that you offload EDT pacing in the hardware. So when it is done in Linux kernel, EDT pacing is done per flow in the FQ disk. So do you mirror this per flow mechanism in the hardware? And if so, when in the kernel, its identity of the flow is defined by the socket for local traffic or by a hash for forwarded traffic. So how this identity of the flow is transferred to the hardware for flow? Thank you.
Yeah, good question. I think we should have mentioned. So the hardware has to have large flow tables and classification of packets to a particular flow. It's the flow itself where either a metadata coming from user with the packet that says when a packet needs to be scheduled, like in the EDT case, or a flow meter or flow shaper action that is programmed on a particular flow that decides when a packet is launched. So yes, you need to be able to classify different flows so that you can schedule, you can have different EDT value on a flow, given a flow rate or a value provided from the application. So, yeah. So yeah, so before the timing wheel logic, there is the, packet processing block, which has these flow classification tables. In some cases, these flows are, programmed through sideband. These flow rules are programmed through sideband, which we didn't go into the detail of, focus more on the timing wheel aspect of things. But yeah, you have to, if you're not using EDT, which is per packet, you can specify when to launch a packet. If, say, we were looking at the other fixed flow delay case, you have to have flow rules in the hardware which add the exact amount of delay to the packet of a given flow. And, that can be different for different flows. So, yeah. These are exact match tables for flows. No, yeah.
Thank you
They
for
can
the
be 10
presentation.
million.
I also have a question regarding the EDT offload. As I understand correctly, the pacing is offloaded to the card, but still some cycles spent to the ordering of the packet at the with the red battery on the CPU.
Right.
It would be possible to offload that as well, like bypassing the QDisks and put the...
Yes, and right. So that's actually a very good point. Here, I think Priyali was going over this. So the FQ scheduler has to sort between what is available right now and the hardware can take into account, and it's within the now plus offload horizon versus the ones that are to be scheduled later. The was your question about this sorting? Sorry, maybe I might have missed it.
Yeah, so I think I got the question. Yes, so the sorting is a overhead in the fair queue. I think that can be addressed. These patches are not upstreamed yet. Yeah.
So
Since hardware offload means hardware block itself can do the sorting. So yes, it looks redundant. I think this is kept same way because FQ QDisk is also support without does the sorting for other type of not when hardware upload is not supported, it does the scheduling and does the sorting. So just for that sake, sorting is done, but I think we should club it. Yeah.
Just one comment to that.
Did you mean not just the sorting, but ordering in monotonically increasing time for the
No,
packets?
that will be required. That we cannot do omit because we need to make sure that we are not sending beyond the horizon. Right?
Maybe I can
is just a
answer the question. Sorry to interrupt. Eric Demazet speaking. So I implemented a few months back FastPath in FQ. So for this kind of packet, we are not using arbitrary at all. So they are just passed to the device directly. So there is no overhead in FQ. It's called a FastPath. You can look at the Git tree. It was done this year, last year, something like that.
So FastPath, I was not very sure, Eric. Thanks for clarification.
No, it's handling the offload horizon just fine. If you don't have a standing queue, because if you have like a bottleneck, like the line rate and the queue disk is like filling, then yeah, sure, we need to ensure FQ. So we use the arbitrary in this case.
Thank you for the answer, and thank you for Eric as well. I'm mostly interested not in FQ, but for UDP traffic, I wanted to use EDT. And right now, on older Intel NICs with timing wheel support, because the hardware cannot reorder the packet based on the timestamp, if you messed up the order of the timestamping, you ended up a FIFO behavior with head of line blocking of the oldest timestamp. And I think you get it, what I'm
Yeah. No, I do get it. That's definitely the case for older devices like i210, which supported SOTX time. but they did not support something called out of order completion. And that's why you had to, um, um, uh, put the timestamps in an increasing order when you're submitting it to the hardware, because your earlier packet gates the later packets from being scheduled in the hardware, or for hardware to kind of schedule it at an earlier time than the packet ahead of it. So this is where I was mentioning that hardware actually supports a different queuing scheme, where the buffer completions and the descriptor completions are separated out. So you could have, like in this case, the yellow packet, which is completing before the rest of your blue packets, although the blue packets here were scheduled on the device earlier, right? Because the yellow packets time, EDT time, is earlier than the EDT time of these blue packets. So
yeah, but there
definitely,
is also another side to this coin, because if you have a malicious software that tries to put the packets with the timestamps far in the future, then your FIFO will get stuck with a lot of
no,
packets
because
that won't be sent soon if you
no,
don't
that's
have
where
this safety layer.
the packet drop, right? If it is above the horizon, you will just be dropping those packets. So yes, you could
Yeah, but
still fill
that's
up
the
your
mechanism specific to the device, right? It's not a generic behavior defined somewhere. That's basically also one of the reasons why this scheduling of only small window of packets that will be sent in the future is implemented.
right.
Okay, I think, can we wrap it up here, please? Thank you.